Hello everyone. In this lecture, I'm going to give you a special presentation on big data. I guess most of you have heard of this term big data from places like professional articles or newspapers or even TV shows. But from those reports, they describe big data as some magic. They simply focus on the application of big data, what it can do in terms of making profit, in terms of relying something. But there is no comprehensive discussion of big data. So in this lecture, I'm going to systematically describe big data and help to give you an understanding of what it is. This is the outline of my presentation. I will first discuss the status quo, so how much data we have today, and then I will introduce the definitions of big data, how to define big data. And after that, we will touch up one base on why big data emerges, why we have so much data. And then after that, we will talk about opportunities and the challenges associated with big data. After the first part, I will introduce how big data and auditing can be related. Then I'm going to discuss an example application of big data in auditing, and it is called process mining. In the last section, which I want to emphasize, is that we need to have some cautions when talking about big data, especially when trying to apply it in auditing domain. So how much data we have today? Well, in 2010, we have 1.2 zettabytes of data. Well, you may not be familiar with this scale, but to put it in a way that you should be familiar with, it equals to 1.2 billion terabytes. If you go out and want to purchase an external drive, typically you will get one with 1 terabyte or 2 terabytes, and sometimes if you pay more, you can get 4 terabytes external drive. So this is a huge amount, 1.2 billion terabytes. And this number increased about 50% in only 1 year. So in 2011, we have 1.8 zettabytes data. This data is not up to date, so probably now you can have the total amount of data generated in 2013, but it is expected that by the time of 2020, we will have 40 zettabytes of data. This is enormous. And then let's take a look at some internet statistics. So for Google, we all do Google search, and it is estimated that there is over 1 billion queries per day. So what does this mean? This means that for people who have regular access to computers or tablets or laptops, they conducted at least one query per day. And for YouTube, this is even larger. There are more than 4 billion views per day. And on Facebook, there are 8,000 million updates per day. For Twitter, there are 250 million tweets per day. And of course, this is just a part of the view, and you can list many other statistics, like the number of transactions on Amazon, like the number of updates on Instagram posted per day. Well, actually, the amount of data is not the scariest thing. What's surprising is that more than 90% of all available data was generated in the last 2 years. So basically, in the last 2 years, we generated far more data than we had before in the whole human history. And this trend is expected to continue because both individuals and companies regard data as its biggest asset and is trying to collect more data, although they cannot handle it for the moment. For example, they collect all kinds of video stream data, they collect all kinds of image data. Although the technology today cannot efficiently handle them, but still, those companies believe that someday in the future, they will have some value. Now let's take a look at this three-phase model of big data. Although there is no common definition of big data, but this three-way model is widely accepted in both in newspapers and professional articles. It is to characterize big data in three dimensions: data volume, data variety, and data velocity. It was first introduced in 2001 by an analyst at Gartner. So now let's first take a look at the data volume dimension. Go back to like 10 years ago when we were talking about the size of the data, we sometimes said, KB, kilobytes, and we would feel that it was actually pretty large. But now, I guess you are more familiar with megabytes, MB. If you install Microsoft Office on your laptop, it typically takes like around 800 megabytes. Then we feel this is not enough, so we go to the next level with gigabytes. Typically, the space of your hard drive on your laptop is around several hundred gigabytes. Then, as I mentioned before, if you go out and purchase external drive, the space you will get is typically 1 terabyte or 2 terabytes. And after that, we have petabytes, and we can even go to the next level, and finally zettabytes, and even go further, one can go to YB. Apparently, the data volume is increasing, which is one feature of big data. Then let's take a look at another dimension, data variety. So traditionally, we have structured data that is stored in relational database. So RDBMS means Relational Database Management System. Structured data refers to the kind of information that can be stored in a table. So typically, we have columns, which represent the variable, and we have rows, which represent observations. But this format of data cannot capture everything in our life. For example, like email is one kind of unstructured data. And also your social network is another example of unstructured data. Because in a relational database or table, it is very difficult to describe the relations between people. And then we have data like images and videos. And I think it's understandable that such information cannot be stored in a relational database. When you are trying to do a search online for video, typically you type in the keywords, and if that keyword matched the keyword provided for that video, then you can find it. but those keywords are manually assigned to that video by human beings. If you want to search something, search something appeared in the video but has never been assigned to that video, then it would be impossible. Now, of course, we have techniques such as facial recognition and some advanced techniques that can help us to automatically recognize information in the video stream, but it is not available to the public. So we need another way to store such information and index such information. For example, images is typically stored in the unstructured database and is indexed by using R-tree. If you are interested in it, you can search this term, R-tree. And the last dimension is data validity. In the past, when a company is trying to analyze its own data, typically it will do it in a batch mode. What's a batch mode? Well, it means that, for example, every day at exactly 11 o'clock, I will upload my information to my system and my analysts will analyze that. So it is not done in real time. But today, of course, every business is conducted in real time and even the analysis. Basically, if you make a purchase order online, the system of that company on the back end will automatically update all the associated tables and even for the tables that are used by analysts so that they may automatically analyze the results or they may have people to analyze it in a later stage. So all these three dimensions contribute to big data phenomenon. So now we need to answer another question. Why there is so much data and why the amount of data is increasing tremendously in recent years? Well, while there are multiple factors that contribute to this phenomenon, here I summarized three most important factors. The first one is that we have various applications that generate a large amount of data. So, for example, we have cameras that is deployed and distributed all around the world, and there are millions of them. Each one of them is continuously recording and capturing videotapes. This creates a large data repository. And also imagine the satellites. If you can remember the Malaysian Airlines 370 tragedy, there was a case that a satellite company was asking for volunteers to analyze and visually inspect those images they captured by satellite. So this is to say that also we have satellites taking pictures all the time that also generates a large amount of data. And also we have sensors. We have sensors to measure like temperature at different locations. We have sensors to measure like humidity and other stuff. We also have Internet of Things. Well, Internet of Things, basically it is to say that all the electronic equipments or devices are exchanging and sharing information together and to create a smarter world. Suppose that your refrigerator is connected to your watch and you have frozen meat in your refrigerator. Then somehow, before you go back home, your watch sensed such information, so it will transmit that to the refrigerator And then the refrigerator will start to unfreeze the meat so that when you get home, you can take out the meat and cut it without any effort. Under such cases, in such a scenario, every device is recording and generating data. And one thing that I have to mention is smartphone. Smartphone is actually the biggest sensor deployment in the whole world. It can track your movements and record what happened. If you want to use any location services, it will record your location, and many people will use smartphone to search on the internet, will take pictures and videos, and all this generate a large amount of data. This is combined with the popularity of social networks such as Facebook or Instagram, because people are actively participating in social network by sharing photos, by talking about what they saw, which creates a large data repository. So this is one factor, and the other factor is that the storage capacity has increased significantly. In the past, like even 8 years ago, if you say you have 1 terabyte of data, that would be difficult for most individuals to store. But today it's quite simple. And actually, statistics show that the storage capacity is doubled every 14 to 18 months because we have better capability to store the data. So definitely we are able to host more data, and we will have more data ready to be analyzed. And the third contributing factor is that research in data mining, machine learning, and information retrieval can transport data into knowledge. So these fields has witnessed significant progress in the recent 13 years, and thanks to these technologies, we can better use big data. For example, Netflix is using one technique called alternative least square to provide better movie recommendations to customers. Because of these technologies, people and companies will have incentive to store a large amount of data. So the next question is, should we embrace big data, or are we embracing big data? The answer is yes. Actually, the US government has initiated a big data initiative in 2012, like it's said here, aiming to make the most of the fast-growing volume of digital data. The Obama administration today announced the Big Data Research and Development Initiative. By improving our ability to extract knowledge and insights from large and complex collections of digital data, the initiative promises to help resolve some of the nation's most pressing challenges. To launch the initiative, 6 federal departments and agencies announced more than $200 million in new commitments that promise to greatly improve the tools and the techniques needed to access, organize, and glean discoveries from huge volumes of big data. And not only US government, but also companies are embracing big data phenomenon. There are hundreds of startup technology companies that developing technical solutions to handle big data, And also those giants such as Amazon, like Google, like Facebook, they are not falling behind. They are making a large investment in developing the technology in handling big data and also investing in constructing the underlying infrastructure. For example, like the Hadoop system, which we will discuss later. When talking about big data, there are several misconceptions that I want to highlight here. The first misconception relates to the name of big data. So how big the data should be to be considered as big data? Well, like for an individual, if you have 1 terabyte of data, you would say, oh, that's big. But actually, if it's for NSA or NASA, 1 terabyte of data is nothing, it's trivial. They can analyze the data in a fraction of time. So the first point is size is relative. It is related to the resource that you have available. So the second point is that the type of data matters. Suppose you have 1 gigabyte of data. One is in structured table format, and another one is just image. Of course, you can analyze the tabular format in a reasonable time, but you will have extremely difficult time in analyzing the image. So the type of data matters because different types will lead to different results, and you will take fundamentally different amount of time in analyzing different types of data. And the third issue is big data all about time? Sometimes we would say, well, big data is good, but we need to know that if we cannot deliver and transform big data into knowledge in a quick time, then it may be not valuable at all. Suppose that Amazon is analyzing your click-through and your visiting patterns to provide you a better recommendation. If it takes like 10 minutes for Amazon to complete it, then it means nothing because the customer has already left. So time is definitely important in big data. And the fourth point is big data all about analytics? Well, for a company or any researcher, we would say that big data analytics is the most important step because we only care about the final output, the knowledge. But because big data is so big that it requires changes in the underlying infrastructure of those, not only the storage but also the processing. So without underlying such infrastructure, big data analytics would be impossible. Well, the last one relates to the question of should we store whatever data we can. Well, some may say that since you have, seemingly unlimited storage capacity, so you should store whatever data you can store. But this is not necessarily true because even though you can store it, some data may be so messy that if you want to use it, you need to require large amount of time of analysts in reprocessing the data to a point that the value you can possibly obtain is less than the efforts that you exerted. So this, combining all this information together, we lead to one more rigorous definition for big data. This is from UC Berkeley. It says, big data is when the normal application of current technology doesn't enable users to obtain timely, cost-effective, and quality answers to data-driven questions. So the fundamental thing about this definition is that you should always relate big data to your available resources.
Now let me share with you some examples of government efforts. So this one is called the Global Pulse. Global Pulse is an innovation initiative of the United Nations Secretary General on Big Data. Its mission is to accelerate discovery, development, and scale the adoption of big data innovation for sustainable development and humanitarian action. So the initiative was established based on a recognition that digital data offers the opportunity to gain a better understanding of changes in human well-being and to get real-time feedback on how well policy responses are working. From their perspective, they are not interested in making a profit from big data. Instead, they want to monitor the reaction and what happened in the society in real time through the lens of big data. As I said before, people on social media, they actively share what happened to them and what they saw. So this creates an opportunity for the government to monitor what is going on there. And the Global Pulse functions as a network of innovation labs where research on big data for development is conceived and coordinated. So they have scientists all around the world. Some scientists are hired by United Nations. They work exclusively for United Nations. But some scientists are like researchers, but they voluntarily participate in such a project because they believe this is something that is good for the whole society. So Global Pulse has appointed different roles, such as a coordinator and a data collector. So the data collector will go around the world, talk with large companies, and to obtain the data. And for the coordinator, basically they will coordinate different scientists in different countries and distribute the workload. There are two keywords in Global Pulse initiative. One is big data, the other one is real time. Well, because they are governmental entities, so they have wider access to large amount of data. So as I listed here, they can obtain data from social media, online sources like Twitter, like Facebook, like online forum, and etc. They also form private sector partnerships with Google or online banking. So they send people to these large companies to persuade them providing useful information. And this is also an advantage of working for United Nations because otherwise there is no way that you can get online banking data. And they also incorporate physical sensors data in their analysis. Like I explained before, they use sensors to measure temperature, they use sensors to measure humidity, and they also monitor the traffic in real time. Besides that, they also have crowdsourcing reports. So basically, they will have the results of survey with answers to questions in the questionnaire to obtain an idea of people's opinion on different issues. The second keyword is real time. So why Global Pulse want to do this in real time? Well, this is because they have different objectives as researchers. So as a researcher, what we typically do is to obtain the data, reprocess it, analyze it, and then if we find some interesting patterns, we write it into a paper and publish it. That's the whole purpose. But for global pause, the most important objective is to speed up the public sector's ability to understand where people are losing the fight against hunger, poverty, and disease, and propose plans to combat when it is not too late. Without using big data, our governments are typically slow in reacting to disasters like this, but after using big data, hopefully we will speed up the process so that people all around the world will suffer less. This is an example project that is conducted by Global Pause. It's called Unemployment Through the Lens of Social Media. The purpose of this project is to investigate whether to and how the feelings and information shared on social media and other online user-generated content could enrich understanding of the effect of changing employment conditions on people's perceptions and decisions. We know that unemployment rate is an important indicator of the stability of the economy. Although we obtain unemployment rate data every month, but it is like the after-fact data. We don't know it in advance. If the unemployment rate is high, this could create potential problems, and the government is always trying to combat with this issue. So the target country where they obtain the data is from the United States and Ireland for two reasons. First is that both countries have a high usage level of social media and blogs, so the people there are more likely to share their feelings on social media. Second, they are both experiencing unprecedented fluctuating unemployment rate, especially in the US. The standard deviation of unemployment rate is very high. So this project is trying to see if they can predict or know in advance the unemployment rate through the lens of social media. So this diagram shows the process of the whole project. First, online job-related conversations from blogs, from online forums, and news were automatically retrieved, and each document was assigned a quantitative mood score based on the tone and mood of the conversation, which I will discuss later. And also, the number of unemployment-related documents that also dealt with other topics, such as housing and transportation, was also quantified and categorized. After that, the aggregated mood scores and the volume of conversations around the different topics were compared with official unemployment statistics over time to see which factor has predictive power for the future unemployment rate. So this is the detailed procedures of this project. First is data acquisition. So they extract the sample data from a variety of public internet sources over the past 2 years. Documents are considered to be relevant if they contain terms defining unemployment, including unemployed, fired, on the dole, and etc. Basically, they define a dictionary, and by mapping the words in that dictionary to the documents, they can extract unemployment-related documents. And of course, the dictionary was developed by domain experts. And then the next step is called filtering. The documents are categorized into one or more topical categories, like housing, transportation, entertainment, consumer spending bills, financial distress, underemployment rate, alcohol, education, healthcare, travel, and etc. And there is also another validation step, is that all the selected documents underwent a series of validation rounds to ensure the quality and the accuracy of the cure and the filtering process. This step works like a noise removal. Now, after all the reprocessing, we come to the important part called sentiment analysis. Each selected document was evaluated with sentiment analysis techniques, a form of automated text analysis that assess the nature of the content through the natural language processing and the linguistic rules. Well, this sounds, complicated, but the basic idea is very simple. So we have some publicly available dictionary that can classify words into positive and negative. So by using such a dictionary, you can give any document a score of sentiment. But in this case, they didn't simply classify it into positive or negative. They have many categories like anxiety, confidence, hostility, confusion, energy, and happiness. Apparently, they are using a dictionary that they developed themselves. After assigning each document a score, then they do cross-correlation analysis. This is to correlate all the indicators like the sentiment, like the volume of the discussion with the real unemployment rate information to see which one has predictive power. And here, this figure shows two variables. So the dot line is the topic on public transportation, and the blue line, or as you could see, the green line is unemployment rate. We can see that the volume of discussion on public transportation spike on months or 2 months prior to a spike in unemployment rate. So this serves as an indicator. And this is the summary of this project, the results they obtained. The quantified mood scoring was correlated to the unemployment rate to discover leading indicators that forecast rises and falls in the unemployment. In Ireland, confused mood was correlated with unemployment rate with a lead time of 3 months. In the United States, hostile mood was correlated with unemployment rate with a 4 month lead. So notice that there is a difference between different countries. And it is also possible that if you go to the next detailed level, there will also be a difference between different states, like the people in Texas, what they feel before unemployment could be quite different from what people in New York will feel before unemployment. And they also find that the volume of documents related to coping mechanism showed a significant relationship with the unemployment rate. In the United States, conversations about the loss of housing increased 2 months after unemployment spikes. We also have other famous examples, like the first one, was from a paper published in 2011. It said that Twitter mood can predict the stock market. Basically, after the analyzing the overall mood displayed on Twitter, they found that if they incorporate this mood variable into stock prediction model, its accuracy increased significantly. But not all mood has such a power. They identified that mood like calm and happiness have predict power, but not anger or anxiety. And this is one very interesting paper. The next example is called public health surveillance. This is an ongoing project at Rutgers University in collaboration with medical school. They still use social media, but for different purpose. So it is to see whether they can use big data to predict or prevent any outbreak of diseases. So let's take a look at the detailed level. First, they extract tweets from Twitter, and this procedure is done by identifying the keywords that are related to symptoms. This is to say that if those tweets contain exact symptom words or some words that are highly associated with symptoms, then they will be extracted. For example, if I send a tweet saying I have a headache today, then that tweet will be extracted. And after this, they will conduct noise removal and filtering. And notice that for Twitter, they not only extract the tweet information, but they also extract the geographic location. After the reprocessing, they store the content of the tweets and the geographic location in an event database. They also collaborate with local hospitals' records and the CDC's report to see if there is any correlation between these two. For example, if there is an increasing number of patients in hospital, then they can use this database to infer the dependencies. For example, if it could be that most of the patients went to the same place to have dinner, then that could be the cause of the sickness. And also they can conduct predictive analysis. For example, if several people indicated that they have fever and the geographic location data shows that they all went to the same place, then there could be a problem at that place, and so we can the CDC will know it and possibly send someone there to examine the issue. I think this is critical, especially under today's scenario, the outbreak of Ebola. Of course, this process involves some advanced techniques such as machine learning, and if they can confirm or with a high level of confidence that there is a problem in certain area, then they can send text messages to subscribers to alert this issue.
While big data has many benefits for governments or companies, we have to realize that there are some technical challenges or technical issues that are underlying big data. The rapid increase of data poses significant challenge to both hardware and software infrastructure. Let's first talk about hardware. I explained before that the storage capacity is increasing at a rapid speed, and it is doubled every 14 to 18 months. However, this speed of increase will not be expected in the future because of some physical limits. And this is also true for the processing power of our computer system. So some physics laws, such as Moore's laws, tell us that when the number of units within a fixed space has increased to a certain limit, then the heat will prohibit all the units functioning as it should be. In other words, we cannot achieve the expected maximal utility. Because of this problem, so to efficiently deal and handle big data, what we typically do today is to distribute the data across different nodes. One node could represent a computer or any device. The analytics is also conducted by coordinating the work among different computers. So this poses a challenge for the algorithm design and business model. You may not be familiar with algorithms design, but imagine when you are typing a code in R or when you are doing like the sorting in ACL or IDEA, there is underlying code that supports that function, but they are designed to support traditional data, not big data that has such a large amount. So the algorithms need to be revised. And we also need algorithms that can distribute the workload to different computers. And after each computer finishes their part, the algorithm also needs to aggregate the results and obtain the final results. In terms of business model, we all know that today we talk about cloud computing, which is to outsource part of the function to a third party. So in this case, you don't need to purchase the software and run it yourself. Instead, you can just, give your data to a third party and they run the software. They run the analysis and return the result for you. You don't need to worry about the maintenance of it. But is this optimal for all companies? Definitely not. So we also need to understand better of this point. In terms of algorithm, if you have read any professional IT articles related to big data, you will see these two terms, MapReduce and Hadoop. Hadoop is software for data-intensive distributed applications based in the MapReduce programming model and the distributed file system called Hadoop distributed file system. Well, this seems complicated, so what I'm going to do is to show you a video that describes how MapReduce and Hadoop work in the world of big data.
Hi, I'm Bill Appleby, and today, in 7 minutes flat, I'm going to explain how Hadoop works and what you can do with it and what big data is. I've done a lot of big data projects in Australia, in Canada, in the United States, and I'm also a Learning Tree instructor. Okay, so why big data? Firstly, we all know that governments and businesses are all gathering lots of data these days. Movies, images, transactions. But why? The answer is that data is incredibly valuable. Analysing old data lets us do things like detect fraud going years back. These days too, disk is cheap. We can afford to keep all that data. But there's a catch. All that data won't fit anymore on a single processor or a single disk. So we have to distribute it across thousands of nodes. But there's a good side to that. If it's distributed and we run in parallel, we can compute thousands of times faster and do things we couldn't possibly do before. And that's the trick behind Hadoop. Okay, how does Hadoop work? Suppose what I wanted to do was look for an image spread across many hundreds of files. So first off, Hadoop has to know where that data is. It goes and queries something called a name node to find out all the places where the data file is located. Once it's figured that out, it sends your job out to each one of those nodes. Each one of those processors independently reads its input file. Each one of them looks for the image and writes the results out to a local output file. That's all done in parallel. When they all report finished, you're done. Okay, we've seen one simple example of what you might want to do with Hadoop, image recognition. But there's a lot more to it than that. For example, I can do statistical data analysis. I might want to calculate means, averages, correlations, all sorts of other data. For example, I might want to look at unemployment versus population versus income versus states. If I have all the data in Hadoop, I can do that. I can also do machine learning and all sorts of other analysis. Once you've got the data in Hadoop, there's almost no limit to what you can do. Okay, we've seen that in Hadoop, data is always distributed, both the input and the output. There's more to it than that. The data is also replicated. Copies are kept of all the data blocks so that if one node falls over, it doesn't affect the result. That's how we get reliability. But sometimes we need to communicate between nodes. It's not enough that everybody processes their local data alone. An example is counting or sorting. In that case, communication is required. And the Hadoop trick for that is called map reduce. Let's look at an example of how map reduce works. What we're going to do is take a little application called count dates that counts the number of times a date occurred spread across many different files. The first phase is called the map phase. Each processor that has an input file reads the input file in, counts the number of times those dates occurred, and then writes it as a set of key value pairs. After that's done, we have what's called the shuffle phase. Hadoop automatically sends all of the 2000 data to one processor, the 2001 data to another processor, the 2002 data to another processor. After that shuffle phase is complete, we can do what's called a reduce. In the reduce phase, all of the 2000 data is summed up and written to the output file. When everybody is complete with their summations, they report done and the job is done. Okay, we've seen a couple of great examples of how Hadoop works. The next question is, how does Hadoop compare to conventional relational databases? Because they've dominated the market for years. We've seen one big difference, which is that in Hadoop, data is distributed across many nodes and the processing of that data is distributed. By contrast, in a conventional relational database, conceptually all the data sits on one server in one database. But there are more differences than that. The biggest difference is that in Hadoop, data is write once, read many. In other words, once you've written data, you're not allowed to modify it. You can delete it, but you can't modify it. By contrast, in relational databases, data can be written many times, like the balance of your account. But in archival data, which Hadoop is optimized for, once you've written the data, you don't want to modify it. If it's archival data about telephone calls or transactions, you don't want to change it once you've written it. There's another difference too. In relational databases, we always use SQL. By contrast, Hadoop doesn't support SQL at all. It supports lightweight versions of SQL, called NoSQL, but not conventional SQL. Also, Hadoop is not just a single product or platform. It's a very rich ecosystem of tools and technologies and platforms, almost all of which are open source and all work together. So what's in the Hadoop ecosystem? At the lowest level, Hadoop just runs on commodity hardware and software. You don't need to buy any special hardware. It runs on many operating systems. On top of that is the Hadoop layer, which is MapReduce and the Hadoop distributed file system. On top of that is a set of tools and utilities, such as Hadoop, which is statistical data processing using the R programming language. There is a machine learning tool. There are also tools for doing NoSQL like Hive and Pig. And the neat thing about those tools is they support semi-structured or unstructured data. You don't have to have your data stored in a conventional schema. Instead, you can read the data and figure out the schema as you go along. Finally, we have tools for getting data into and out of the Hadoop file system like Sqoop. That ecosystem is constantly evolving. So for example, there's now a new tool for managing the pig tool called Lipstick on a Pig. And there are many more, and that environment keeps being added to all the time. So now we've seen how Hadoop works and what it can do. I'm sure you've gotten more questions than that, such as how do I install Hadoop and on what platforms? The differences between different Hadoop versions, or how to do extract, transform and load in Hadoop. Answers to those questions are on our website at the following URL. I really hope you've enjoyed this video. Take care.
Here I listed some other applications of big data in different fields. For example, it can be used in environmental modeling. It can be used in modern transportation. I think you have already benefited a little bit from it, because some devices, some maps can automatically adjust the route based on the real-time traffic information. And also it can be used even for computer security by analyzing the logging information. This is an example that I will show at the end of this lecture. While we have seen so many benefits of big data, there is a fundamental question. Are big data always better? Are big data always better than traditional data? Well, the answer is no, this depends. The first point is that big data comes with bigger noise. Sometimes noise could result in bias in your analysis, so we have to filter out these noises before analysis. But this step is time-consuming and could consume a lot of resources. And the second point is about representativeness. I think this can be better demonstrated by using a Twitter example. In many studies, no matter in accounting, in finance, or in market study, many researchers assume that people on Twitter are representative of the total population, which is not correct. A good example happened in 2012 when Hurricane Sandy came. At that time, the Twitter data shows that people in Manhattan tweeted most of the tweets during that period. So if you don't consider the representativeness problem, then you'd see that Manhattan is the area that suffers most of the damage, but which is not true, because the results on Twitter is partly because first, people in Manhattan are more likely to use cell phones to tweet information, and also they have a higher coverage of cell phones. And the third point is accessibility. This is to say that by using big data, we can study and understand the person's life and even personal life very well, and this would result in many problems. The person may not want to be studied, but he has no choice. So there is ethical problem involved in big data. And the last point is that big data will create a new form of digital divide. So traditionally, we say digital divide, we mean people with access to computational technology can do things efficiently and effectively, and this will create a divide and bring up some issues. And here, big data can create a digital divide between companies and individuals. So suppose large companies like Facebook, like Amazon, like Google, they have large amounts of information that enables them to understand their customers, to know the changing human behaviors so that they can provide better product. But this is not possible for any firm that does not have such a large market scale. So this is a new form of digital divide between companies. Now I'm going to tell you the overall process of big data analytics. But before that, I want to mention this paper, Scaling Big Data Mining Infrastructure, the Twitter Experience, which was published last year by two employees working at Twitter. So they shared their experience what they were doing at Twitter for data analytics. They said that the analytics platform at Twitter has experienced tremendous growth over the past few years in terms of size, complexity, number of users, and variety of user cases. Previously, there are less than 10 people in Twitter that work as data scientists, but now they expanded a lot. And they said successful big data mining in practice is about much more than what most academics would consider as data mining. As a researcher myself, I would think that data mining is to apply algorithms on the data and to interpret the data. If you can find something that has never been found before, or you can find some results that is contradictory to existing beliefs, then that is knowledge. That is the beauty of data mining. But they said, well, yeah, this is important, but actually most of the time is consumed in preparatory work to the application of data mining methods and turning preliminary models into robust solutions. They mentioned that more than 80% of the time is to prepare the data for analysis. Many of you may think that data scientist is a fancy job because you can torture the data and obtain some knowledge. But what they said means most of the jobs are boring. They have to prepare the data. And this is not something that you can easily outsource because preparation of data is highly related to your final analysis. This paper also shared something else when they were analyzing data at Twitter. I think it's very useful. If you have time, you should read this paper. Now, this graph shows the overall process of big data analytics. But actually, it's also the process of analyzing traditional data. First, we have to acquire the data and record the data. After that, we need to do data extraction and the data cleaning to make the data ready for study. Because in the big data scenario, we have information from multiple sources, so we need to do data integration or aggregation, that to merge all the information from different sources into a manageable data repository. After that, the next step is analysis and modeling, which is a part that many of you may like. And the final part is the interpretation of the result. Many great ideas are generated at this stage. And in every step of the overall process, we will have problems. And here we listed several problems like the heterogeneity, scale, timeliness, privacy, and human collaboration. When you are doing big data analytics, no matter what field you are in, like in IT or in auditing, analysis stage is always only a fraction of it. And you will have many significant challenges extend beyond the analysis stage. The first example could be tracking provenance. So provenance is about how you come to this conclusion. So at each step, what you have done. Provenance can explain how each result was derived and based upon precisely what input, so that if you make an error at some stage, you can easily identify it. This is critical for big data analytics because it requires a lot of efforts and even human collaboration, so that without tracking provenance, when you had a difficulty with something, it would be extremely difficult for you to find the causes of that. And also, we need to handle time-changing frameworks. So these stages are critical for the success knowledge extraction from big data, yet rarely recognized in the public community. When you read something related to big data on The Economist, 99% chance that they will only say what big data helped achieved rather than what problem that big data may have. I'm not going to describe every stage, but I will just highlight some points. First, in the data acquisition and recording stage. Because data were generated from various sources, including social media, simulation results, and sensors, so not all the information is interesting and useful. So we need a filter in place to reprocess the data so that we only analyze the useful information. A filter process could compress the data by orders of magnitude. It can significantly reduce the amount of data that you need to analyze. But the problem is how you can define a filter. If the filter is too stringent, then you will lose many interesting information. But if you set the threshold too low, then the filter didn't make much changes to the original data. One example is that, suppose if the sensor records something deviates significantly from others, should it be filtered out? I mean, sometimes this could be caused by the error of this sensor. So in that case, we definitely need to filter out the results from that sensor. But on the other hand, it could be that that particular area has something special that leads the sensor records this. So this is something exactly what we are looking for. So in this case, it is very difficult to say how we can define a filter. And this field requires active research. Another important aspect in this stage is metadata. Metadata, simply put, is data about data, which describes what data is recorded, how it is recorded, and measured. This is similar to the idea of data provenance, which is the information about data as its acquisition. So data provenance should be carried along through different steps of data analysis because it can help identify subsequent processing dependent on a particular step. In the data cleaning and integration stage, we will also have many challenges. The information collected is not in a ready-to-process format. For example, the electronic health records could contain information like transcribed dictations from physicians, which is handwriting, and we have results from different tests, which is indicated by positive or negative or some numeric numbers. And we also have image data, such as the X-rays. So an integration process that merges underlying sources together and express information in a structured form suitable for analysis is needed. Today, people have realized this problem, but not too many breakthroughs have been made. And in the future, eventually we will analyze audio data, video data, and trajectory data, and how to integrate such information with traditional data to form a holistic picture could be a challenge. In the data modeling and analysis stage, querying and analyzing big data is fundamentally different from querying and analyzing sample data. When we are doing traditional data analysis, the first step is to remove noise. But in big data scenario, noises in big data could be valuable because we can use these noises to disclose hidden patterns in sample. In a sample, some hidden patterns cannot be revealed either because that it is completely removed in the sampling step, or that there are so few instances with a hidden pattern that would not be significant. But we will not have this problem in big data. And also, information redundancy can be used to compensate missing values, checking conflicting cases, and validate relationships. We can integrate information from different sources for the same thing and build a model that is comprehensive. Another important point that need to be made is data mining requires trustworthy and clean data, and at the same time, data mining can also be used to improve the quality and trustworthiness of the data. This is to say that by taking advantage of big data, data mining can be used to infer missing values in fields with confidence. And in the interpretation stage, the challenge would be to examine all assumptions made and retraction in the analysis. There are too many possible assumptions in the model and all errors in the processing. So that's why we need data provenance. And to facilitate this, computers need to provide the ability for users to easily adjust their analysis. For example, you conduct an analysis in different steps. The first step is to sort the data. The second step is to choose those records with a value of larger than 1,000. And the third step is run a regression. But then you find that the result is not good, or you want to replicate the result. So what you need to do is not to go back and start over. Instead, the computer should provide a user-friendly interface that help you to easily change your code. You simply need to revise the 1,000 to 500, and it will immediately run the code again and give you the new result. This can help you to compare the results using different parameters. And lastly, visualization capability for big data should be provided. While we have talked about visualization, but what those tools showed is that we can visualize 3, 4, 5, or even maybe 6 dimensions. But when the data dimension increases to 100, it is impossible for us to do it. And it also requires a large amount of time to do it. So how to efficiently visualize big data is a research problem. There are also some common challenges here. I have mentioned them before. I will not go over every one of them, just some of them. First, the scale. The problem of increasing scale is managed by using faster processors in the past. But we cannot do this because, follow Moore's law, the processing power cannot increase so fast in the future. So we need parallel computing, but the underlying architecture is totally different for parallel computing compared with traditional computing. And also, the shift towards cloud computing requires consideration on how to cost-effectively meet goals of each task. So this is essentially an optimization problem. But in cloud computing, because users don't know what other users are doing, so reliance on users-driven program optimizations is likely to lead to poor cluster utilization because users are unaware of other users' programs. In terms of timeliness, there is a dilemma here. So the larger the data set to be processed, the longer it will take to analyze. But on the other hand, sometimes we need fast response. I have already mentioned the example of Amazon recommendation, but this is also true for credit card transaction analysis. So when I made the purchase, the back end from Chase Bank was actually analyzing the transaction automatically by integrating information from different sources to see whether it should reject the transaction or not. If this takes a longer time, it would be a problem, a major operational problem for the bank. You can find other examples like the real-time navigation and similar problems. In terms of privacy, because the analysis of big data can reveal sensitive facts about a person that he might not want to disclose, so it is very difficult to draw the red line here. And this is something that is related to the cultures, ethics, and regulations. Privacy law has not been formalized yet, but we would expect it to be coming soon in an age of big data. But on the other side of the story is that there is always a trade-off between privacy and the convenience. If you want to keep 100% privacy, then you will have no convenience at all. You cannot benefit from big data. This is true when you are trying to use your cell phone. If you turn off the location services, then there is no way that the cell phone knows you are near the restaurant and recommend it to you. So essentially, you are sacrificing part of your privacy in exchange for convenience. Now I'm going to introduce big data and auditing. But first, I want to share with you the relationship between traditional data and big data. So first, for auditing, we have traditional data, and this could be like transactional data that we have, like auditors usually obtain. And then we have ERP data and legacy data. ERP data could be information like the logging of different users. Extend this, we have scanner data. Well, by using scanner data, we can answer several questions, like what products relate? Can you predict results? What did you buy? Can you control inventory online? Can you keep real-time inventory? And can you audit inventory real-time? So because scanner is widely distributed in production line and every component will be scanned using the scanner, so scanner data could be very efficient in auditing. Beyond this stage, we have web data, where web data can provide rich information. It will give us the click path of your visit. When you are trying to do anything online, the website will record what you have done, like which page you have rated before and how much time you stayed on that page. And to tell you an even more scary problem, it can record where is your mouse at what time. Online retailers have been using such technique for a long time, to analyze customers' behaviors. And then to the next level, we have mobility data, which is the data generated from your cell phone. I have mentioned this before. It can track your whereabouts, where you are. And for another type of rich information, we have videos, like security videos, news videos. For example, on the first floor in the front door of Rogers Business School building, we have security cameras running 24 hours to capture everything happening there. And we will also have news videos that can reveal what CEOs or CFOs said in public. The other type of data is social media data or corporate emails. Well, this is a kind of data that can describe the relationship between people or people and the company. This could be useful in identifying fraud. So for an auditor, the central problem in this context is to link such rich information back to the traditional data so that they can make sense and better understand the traditional transactional data. This is how big data can fit into audit domains. Now let me explain this in detail. First, what's big data in auditing exactly? Well, auditors already have access to large volumes of transactional data from the firms that they are auditing. So if you read the newspaper, probably sometimes you will see that a very large amount of transaction data could be considered as big data. But in my opinion, a very large volume of transactional structured data in auditing from its client should not be considered as big data. So we need another definition. And here we use a definition proposed by Connolly in 2012, which says that big data equals transactions plus interactions and plus observations. So transactions, the traditional data, are highly structured information, and interactions are data about how people and things interact with each other or with the business. This is a kind of data similar to social media, social network, or corporate emails. And the last type of data are observational data, which tend to come from the Internet of Things, such as RFID, which is a small chip that was placed in almost every product to uniquely identify that product. And also could be GPS, CCTV cameras, and automated monitoring. The next question relates to how auditors can use big data. Accountants are responsible for gathering and reporting information that is useful to management. Then there is a role for them in big data and data analytics. But particularly for auditors, auditors should seek verification of transactions, not with just an invoice or receipt, but multimodal evidence that a transaction took place. We know that auditors are concerned about audit assertions such as existence, completeness, valuation, and auditors will test all these assertions using whatever data they have. Auditors can also analyze textual data because for companies there are thousands of documents that can be analyzed with the help of technology because it is possible to automatically extract such information. We know that audit firms typically are understaffed, so there is no way that they can ask auditors to manually review all the documents. But these documents could provide rich information regarding the firm and its transactions. So with the help of technology, it auditors are able to make sense of this type of big data. In addition, information from textual sources can be used as audit evidence. For example, like information on newspapers, on social media, and blogs. Imagine if there is a news story, a bad story about a client, about an audit client on Wall Street Journal, but the auditors fail to find that report, and then the client indeed has financial difficulty in the future. So in that case, auditors are very likely to face litigation because they fail to notice something that Wall Street Journal has noticed. This alerts auditors that they should also integrate information from like newspaper into their audit evidence. Like I said before, to verify the existence of transaction, the invoice itself is not enough. Auditors can use photo, video, GPS location, and other metadata that could accompany transaction data to increase the confidence that that transaction indeed happens. And also, in terms of valuation, real-time information can be used to justify the valuation of the transaction. In addition, corporate emails can be used to identify potential fraud. It can serve two purposes. One is that it can identify the relationships between employees. And the second one is that the content in that email could be indicative of potential irregularity. Analyzing corporate email is totally feasible because SEC has mandated public traded companies to store their corporate emails, all the emails, for several years. And lastly, sensors and RFID can be deployed to count inventory. Because we know in the observation of inventory, auditors typically will take sample locations and to only examine a sample of inventory. And this is very risky. Instead, if we can extract information from sensors and RFID in the analysis, then we don't need to spend much effort in physically observing that inventory. The information in these devices will help auditors to confirm the existence of inventory. But of course, you can see that information on sensors and RFID can be manipulated, but this is another story. I mean, at least if you are using this kind of information, you can increase your confidence in your judgment. Now I'm going to give you an example application of big data in auditing. This is to use ERP information to identify potential control failures. This is a work that was conducted at Rutgers University and was published this year on one of the top 3 accounting journals. The data they use is event log. So what's event log? Well, an event log is chronological records of computer system activities which are saved to a file on the system. Process mining of event logs is a method that has been deployed over the last decade by computer scientists and statisticians to provide a way of understanding how complex business processes operate. An event log is like a metadata that is automatically generated by the ERP system in a company. What is particularly promising about the event log as a basis for analytical procedures is that it consists not only of data entered by the auditee, but also metadata that is recorded automatically and independently of the persons and the process whose behavior is the subject of the audit. In traditional analytical procedure, what we typically do is to compare different numbers, to compare different ratios, to identify potential deviation and increase risk in that area. But all these numbers are provided by the client firm. In other words, they are not objective and are subject to manipulation. But event log is totally independent of the firm so that it provides a unique view of the company's system and its control. In the company, each user is required to log into the ERP system with his unique password before being able to enter a transaction, and the system timestamps each data entry, even if the originator also physically enters a date. When you want to sign or approve any transaction, you need to first log into the system, otherwise you cannot proceed. And because the timestamp identified by ERP system is independent of the manually entered date, so these two can also be compared. There are several steps of analysis. The first step is to identify the designed process, like which activities need to be included in the event log. In this sample study, they consider a simple procurement and payment activity. And the next step is to create the event log. So you need to create the originator, the timestamps, the initiator, and the approver, and other information. The next step is called process discovery. And this step is very important. While ideally, in the sample case, there would be a three-way match between a purchase order, a goods receipt, and an invoice, which is what you have learned in textbook. The system always allows some flexibility. There could be various reasons for this. For example, sometimes the invoice comes very late after the goods receipt. So to avoid the potential delay in this procedure, so they will approve the payment in advance. And there are other steps such as role analysis, attribute analysis, and social network analysis, which is to identify relations between employees. So this is a standard practice that needs to be followed. It is to first create purchase order, and another one who is different from the first one should sign it, and another person should release this order. And after you have good receipt and invoice receipt to confirm that we indeed get these products, then we go to the next step to pay for these products. So by definition, the control system should ensure that the procedure indeed happens in this step. But this is the result that it showed. You see, you may not see it clearly of what is on these central points, but they are the same as these procedures like sign, release, good receipt. You can see there are so many ways of completing a transaction in this system. The one with the darkest color are the one that they should follow. However, in this ERP system, they identified more than 300 ways of completing the transaction. To give you another idea, they listed the top 20 sequence of this procedure. You can see that the most frequent sequence is the one that follows the template, but for the remaining ones, they all should be considered as violation of control. You may be surprised by this result, but actually it is understandable. For example, management in almost every company, they have the power of overriding the system. So although they are not, although the system will not allow the initiator and the one who signed this order to be the same person, but management can override it and sign it himself. This is something that you cannot learn from textbook, but you need to understand this point as an auditor. But even after talking with the management, with the client, after excluding some sequence that they considered to be legitimate, there are still some sequence that they cannot explain and they thought that are suspicious. So to better understand this, they conducted social network analysis. So there are 175 cases by 3 individuals violating segregation of duties control on release and goods receipt. Although sometimes management can override the system, but there are some things that they should not override. For example, purchase order must be signed and released by 2 distinct and authorized persons, thereby approving the order for release. And similarly, the good receipt and the invoice receipt should be handled by 2 different persons. Although this should not happen in practice, but they indeed happen in this ERP system. So these cases could be considered as major control failure and subject to auditor examination. What I want to emphasize in this case is that before this study, no auditor or auditor firm has used this technology to examine ERP systems. So basically, they totally ignore such information and fail to identify such control failures. And this is a very good example of big data application in auditing. And in the last section, I want to talk about one thing that I feel is quite important. The fact that big data is a heated topic anywhere does not necessarily mean that auditors should also use big data. So there is an old saying that extraordinary claims require extraordinary evidence, and the converse is also true. Extraordinary evidence only necessary in response to extraordinary questions. So the central question is, does auditor need big data to answer extraordinary questions? Let's take external audit as an example. We know that external audit opinion is a discrete decision and not a marginal one. What I'm saying is the client, they can either issue qualified opinion or unqualified opinion. And it's not like something that you can score the client on a scale of 0 to 100. So more data not necessarily valuable if they are already beyond the threshold. For example, let's say the decision rule is to give an unqualified opinion if 90% sure that client accounts are in compliance with GAAP. If auditors, by using traditional data, non-big data, are 90% sure that the client is in compliance with GAAP, then what is the value in using big data to raise that probability to 91%? You could say that I'm more accurate, but how you justify the cost of doing that? In addition, big data problems are open-ended, which means that sometimes it is very difficult to tell what variables will prove to be correlated with a dependent variable. In a business setting, even a 1% improvement in drug efficiency or market campaign adds tremendous value for the company. But this is not necessarily the case in auditing. They are not making profit by providing 100% increase in accuracy. Also, business can use big data to experiment with new correlations to see if they add value, but you can hardly imagine that auditors will do that. If they do experiment with their client, then they will face a very high litigation risk. In fact, type of decisions that auditors are concerned with are constrained by accounting rule and regulations and are not open-ended as the optimization of marketing strategies or the causes of heart disease might be. By contrast, most auditing problems arise in a much more ordered environment with less independent variables likely to impact upon the problem. There is very limited utility to be gained from examining non-transaction data or data from outside the company itself when accessing internal controls, gap compliance, and other such typical audit problems. Also, collecting data with a need for it may make sense in the case of scientists or interest companies, but it is hard to imagine that auditors will feel the same way, because one principle of auditors is to be conservative, to reduce the costs, and to be able to clearly justify any decisions that they make. And apparently, imagine the data collected from social media. While it may be useful, but it would be extremely difficult for auditors to justify what they find. While researchers and managers in search of new marketing strategies may tolerate data ambiguity, but auditors are the type of people that are looking for accuracy. Allowing some inaccuracies to slip in is difficult to reconcile with the focus in auditing on data integrity. The largest problem we have with big data is causation and correlating. I cited one sentence here, and I think this is a common view of businessmen on big data. So these two shifts in how we think about data, from sum to all and from clean to messy, give rise to a third change, from causation to correlation. This represents a move away from always trying to understand the deeper reasons behind how the world works, to simply learning about an association among phenomena and using that to get things done. So in a business setting, the ultimate objective is to make profit. If you cannot understand why there is such a correlation, it is not a problem at all. You can simply take advantage of it and implement your marketing strategy. But auditors can never follow this logic. Auditors will be reluctant to base conclusions on correlations that cannot be proven to be based on any kind of causality, because it will increase audit and litigation risks. Let me give you a simple example. If auditor using big data find a correlation between newly divorced employee and overbilling of expenses, so what are they supposed to do with that information? Should they recommend that divorced employees to be subject to great scrutiny or to be fired? It is one thing for auditors to use correlation information to suggest new areas to investigate further, but quite another to institute formal controls based on that information, because verifiability and credibility are vital in auditing if action against particular employees is to be initiated. And the last one relate to the value of big data driving correlations. So there is a famous story of Google flu trend. It is thought to be more timely and accurate than CDC. The underlying logic is that if there are more people actively searching for flus, then there are more people affected by flus. But as we increasingly rely on big data's numbers to speak for themselves, we risk misunderstanding the results and in turn misallocating important public resources. In the Google flu trend case, it once mistakenly estimated that peak flu levels reached 11% of the US public this flu season, almost double the CDC's estimate of about 6%. While Google will not comment on the reason for the overestimation, it seems likely that it was caused by the extensive media coverage of the flu season, creating a spike in search queries. So to conclude, big data is the means to an end, but not the end in itself. We cannot use big data simply because other fields are using it. And the bottom line is, auditors will likely only turn to big data when they are convinced that the limits of what they can do with non-big data have been reached. And lastly, I want to share one video with you which talks about the dangers in using big data.
Good afternoon. I'm taking a slightly different view of big data than the most, I think, talks given here today. I'm from industrial engineering, and in industrial engineering I'm actually at a fairly specific sub-area which deals with modeling human decision processes with economic, psychological, and operations research models in order to optimize system design. Now, I'm very interested in medical issues as well for quite some time, and in this context I'm wondering what actually having big data will do to medical practice and clinical outcomes. Now, obviously, once we have medical data and we have large bodies of these data, we can infer all kinds of things, and now the current use of computers makes accumulating these large quantities of data possible. Now, we obviously have large potential benefits. First of all, one thing we can now easily do is decide or know what happened to a patient in the past. We have access to his or her entire medical record, and we can look at, for instance, actions other physicians did with respect to this patient. So one of the major issues when we coordinate, for instance, the care of complicated patients who are in the care of a number of specialists. Another issue that is possible now we have big data is we can look at clinical outcomes or in clinical histories of large numbers of patients who receive different treatments and use this information to make decisions. So instead of using peer-reviewed research as the basis for evidence-based medicine, we can actually look at all cases of patients who have similar background to the patient we are trying to treat at the moment and see what outcomes we had. Now, this is obviously very, very promising, but could there also be some negative consequences? Now, one issue that may come up and that you perhaps sort of thought of when we heard, for instance, this wonderful talk about Trito, this web-based system, is that when we access large bodies of data, we may reach conclusions that are characterized by the properties of this particular data. For instance, in Trito, we may have lots of patient recommendations, thousands of patient recommendations, talking about the great use of astrological charts for diagnosing certain problems, okay, because they just report these things. So similar biases, maybe less extreme ones, are also possible when we have clinical data that we access directly and not through the peer review process. But I would like to talk about a slightly different problem that might arise when we have big data. Now, the problem I want to address is related to collecting data on hospitalized patients. We now have monitoring, continuous monitoring of patients in the ICU and in surgery, and we are very likely to have large-scale data collection also on hospitalized patients not in the ICU. Okay? In other words, once we have, for instance, wearable sensors. Now, currently, these data are accumulated and they are stored at the ward, or they're not accumulated at all. They're just used on a moment-to-moment basis. But we can think of the option of adding monitor data to a patient's electronic clinical record. This would allow us now to look at what exactly happened to this patient while he or she were in the ICU. Now, obviously, again, this has clear advantages. Okay? I have the detailed history of the patient's hospitalization. I know exactly when certain things happened. And perhaps I can even understand certain clinical developments better. The patient had a seizure at a certain moment in time, and I can look at the record and see what preceded this seizure. So this is certainly something that is very promising in principle. But could there also be some negative effects of having these data stored? Now, to understand a possible negative effect, let me tell you about a story we did some time ago already. But I think the results are still valid as far as I know from talking to physicians and reading the literature. What we did, we looked at nurses' responses to alarms in a neonatal intensive care unit. We hooked up to the monitors in the unit and collected any information we had in the unit, and we placed observer students in the unit who sort of had to write down whenever a nurse approached an infant and performed some action. And we were interested in tying nurses' actions to information they received from the monitors. Now, as everybody who ever visited an ICU knows, there are lots of alarms, especially in neonatal intensive care units. We actually had something like 16 or 17 alarms per hour, which means about every 4 minutes on average there would be an alarm. When we looked at what nurses did, and we coded it by asking what's the probability of a nurse approaching a certain infant within a 60-second time window after an alarm had sounded from the monitor of this particular infant. What we found is that nurses by and large did not go to infants. So we had smaller or shorter alarms and longer alarms, and we find that among the longer alarms, 5 seconds and longer, less than 20% of the cases when we had a cardiac alarm, the nurse went to the infant. In 40% of the cases when there was a respiratory alarm, the nurse went to the patient. And in about 20% when we had a pulse oximeter alarm, the nurse went to the patient. Now, there may be the gut response that says we have a problem. The nurses are doing something wrong. Okay? There is an alarm. Obviously, what we immediately want them to do is go and treat the patient. But perhaps this may be a little bit a simplistic view of matters. Perhaps this is not a problem. Perhaps the nurses are actually doing the right thing. What do we see? We see that alarms are very frequent. Okay? About every 4 minutes or so we have an alarm. And we also know that alarms, in our particular case, were rarely justified. We observed the nurses in this particular study for about 50 hours, and we had not a single case of mortality, of death, or of an extreme adverse event for one of the patients there. So eventually we had lots of alarms, but nothing really bad happened. So Actually, perhaps nurses attending whenever there was an alarm may have had some negative consequences. One main problem we have in intensive care units, and especially in neonatal intensive care units, are infections. And a nurse interrupting treating one patient and going to another patient to see that there is an alarm and there's really nothing happening, all she needed to do is attach a sensor, may actually increase the chances of transmitting some pathogen from one kid to another, or for increasing the chances of infection of the kid she just left behind. Also, when I interrupt an action and I do something else and I have to resume the action, it's likely that I won't quite perform the interrupted actions correctly. I may forget some parts of it. I may actually double certain actions, or I may be interrupted again and I have to do something else. So there may actually be advantages to not responding to all alarms. So when we have monitor information as part of a patient's clinical record, we can probably reconstruct the events that happened to the patient who was attached to the monitor. We can probably know when a nurse approached this patient. She, for instance, may have pushed the deactivate button on the alarm. Now, if we have this data now in this clinical record, and there is an adverse event, the patient dies, what happens in intensive care units, obviously, the patient or the patient's family, in the case the patient is not alive anymore, may request, and probably will be granted by the court, access to the recordings from the monitor. Now, these recordings will now serve as evidence in legal procedures. If we have a nurse in the intensive care unit who did not respond in a timely manner to the alarms before an adverse event, the staff or this particular nurse will probably be held responsible for the consequences of the event. Now, this would be considered in legalese professional negligence by omission by a healthcare provider, okay, which is something which courts treat very severely. And it's very likely that the hospital and the staff will be held responsible for this negative outcome and will have to pay damages. So what will be the likely response of hospital administration when things like this happen? They will probably decide on policies that say you have to respond immediately to a recorded alarm whenever such an alarm happens, because we don't want these records to reflect you not responding to alarms. Okay, so we will have medical staff respond immediately to all indications. And we may actually find that hospital management may implement some quality measures, which are very fashionable, at least in Israeli healthcare systems at the moment, to reflect these immediate responses. Now, the question is this good or bad? And the answer to this question will depend on the relation between the recorded actions and the importance, the clinical importance of the reactions. If the recorded actions, the actions that have to be performed are really the most important actions from a clinical perspective, then this may actually be very good for patients. But if there is actually a low correlation between the importance, clinical importance of actions and their being recorded, then we may find a situation where adding this additional information not only benefits patients, but may actually even hurt them. So just think of the case where the nurse in the neonatal intensive care unit always has to respond to any alarm. Every 4 minutes she has to leave whatever she does, go wherever she has to go, push the button and go back and resume what she's doing. And it's like this is likely to lead to an increase in mortality in this neonatal intensive care unit. So we have a dilemma here. Collecting more information may be beneficial, but it may also have some negative consequences. And clearly, I'd like to argue that big data in medical settings, and not only there obviously, is not only just a technical challenge. It is a organizational, societal challenge, legal challenge in this particular case, which we have to solve if we want to make optimal use of these big data. And here I can, from my research perspective, my main challenge, or the challenge I see for people in my field of research, is to try to predict the consequences of the availability of these data on the functioning of the staff, functioning of the organization, and eventually the welfare of the patient. And obviously to do so, we need to develop some models of information used by medical staff, a little bit maybe in line with the models Avi Mandelbaum presented here, but taking into account individual human behavior as well. So thank you very much.